Okay, so today I am going to be talking about tropical cyclones. I'm first going to talk a little bit about just tropical cyclones in general in the current climate, just their characteristics, what they are, where they form, and then move on to what is the connection potentially between increased greenhouse gas concentrations and tropical cyclones. And so I like to, make that connection with my diagram that we kind of started over here with the Kaya identity and global economic activity is being driven by fossil fuels, which releases greenhouse gas into the atmosphere, which changes global temperature, which then affects things like tropical cyclones, right? It's not like CO2 itself affects tropical cyclones. It's all mediated through temperature. But we can, see this iconically through the cover of An Inconvenient Truth, where they have a tropical cyclone coming out of the smokestacks of probably a coal power plant. So definitely, communication image-wise, showing that they believe there's a connection there, and so we'll talk about that. So first, this is just a little sciencey video on the formation of tropical cyclones just in the baseline climate.
There are three basic stages in the life of a tropical cyclone: its origin or source, the mature stage, and the dissipation stage where it dies out. These occur in a continuous process, not as separate and distinct stages. Each stage may occur more than once during the life cycle as the strength of the cyclone rises and falls. It may reach land, weaken, then go back out to sea where it strengthens once more. The formation of a cyclone depends upon the following conditions coinciding: a large, still and warm ocean area with a surface temperature that exceeds 26.5 degrees Celsius over an extended period. This allows a body of warm air to develop above the ocean's surface. Low-altitude winds are also needed to form a tropical cyclone. As air warms over the ocean, it expands, becomes lighter, and rises. Other local winds blow in to replace the air that has risen, then this air is also warmed and rises. The rising air contains huge amounts of moisture evaporated from the ocean's surface. As it rises, it cools, condensing to form huge clouds about 10 kilometers up in the troposphere. More warm air rushes in and rises, drawn by the draft above. The rising drafts of air carry moisture high into the atmosphere, so that these clouds eventually become very thick and heavy. Condensation then releases the latent heat energy stored in the water vapor, providing the cyclone with more power. This creates a self-sustaining heat cycle. Drawn further upwards by the new release of energy, the clouds can grow to 12 to 15 kilometers high. The force created by the Earth's rotation on a tilted axis, the Coriolis effect, causes rising currents of air to spiral around the center of the tropical cyclone. It is at this stage that the cyclone matures and the eye of the storm is created. As the air rises and cools, some of this dense air descends to form the clear, still eye as the cyclone rages around it. The eye wall, where the wind is strongest, behaves like a whirling cylinder. Cyclones rotate clockwise in the southern hemisphere, anti-clockwise in the northern. The lowest air pressure in a tropical cyclone is always found at the center and is typically 950 millibars or less. The average air pressure at the Earth's surface is about 1010 millibars. Tropical cyclones have significantly lower air pressure than the air that surrounds them. The bigger the pressure difference, the stronger the wind force. One of the lowest air pressures ever recorded was 877 millibars for Typhoon Ida, which hit the Philippines in 1958, where winds reached 300 kilometers an hour. Once formed, the cyclone's movement or track follows a pathway away from its source, driven by global wind circulation. As warm ocean waters feed it heat and moisture, the cyclone continues to enlarge.
Okay, so some of the takeaways from that are that tropical cyclones, well, first of all, they form over water, right? So they're going to be over the ocean. They're tropical because they require warm water and a lot of evaporation. And then also they mentioned the Coriolis force, which is an apparent force that comes about because of the Earth's rotation. And the Coriolis force goes to zero at the equator, essentially because the plane of the equator is parallel to the axis of rotation. So those three things basically describe the pattern of where we see tropical cyclones geographically in the globe. So we see them close to the equator, where we have very warm sea surface temperatures, but not right at the equator. So I've shown that animation a few times of where the most rain falls globally, and it does fall the most right at the equator in that intertropical convergence zone. So there's a lot of thunderstorms there, but not rotating thunderstorms. In order to get these rotating storms, you have to be off the equator a little bit so that you have some Coriolis force. And yeah, so we can basically see that. And then there's some empty locations in the Southern Pacific and the Southern Atlantic, and that's essentially because there are too cold sea surface temperatures there. So you can see that a little bit in a map like this. This is the average sea surface temperatures geographically. And so, this is why we don't get hurricanes and tropical cyclones either on the west coast of the United States, partially because the sea surface temperatures are too low, and also because the atmosphere is actually not conducive to tropical cyclone formation. But you have kind of the same issue down here in the southern Pacific, and then the southern Atlantic as well. There's a kind of a small area south of the equator where it could be possible to get formation of tropical cyclones, sea surface temperature wise. But again, it turns out the atmosphere isn't great for formation there. So we see them the most over these very warm sea surface temperature areas, and we can see that kind of move seasonally. So here's a video that shows. So if these storms require warm sea surface temperatures, then we should see that change with the seasons when the sea surface temperatures are the warmest. And so that's what we're looking at here, going through the months. This 2007, 2008, and you can kind of see that follow the seasonal cycle where it goes to the northern hemisphere, then goes to the southern hemisphere, then goes to the northern hemisphere, then southern hemisphere with those local seasons. So we know the most about, or we hear the most about hurricanes in this country on the ones that hit our East Coast. And so here's just a little graphic showing how often they hit the East Coast and the Gulf states. And so this is a familiar concept, return period. So this is saying how many years you have to wait on average to see a hurricane. And so red is 5 to 7 years. So the lower the return period, right, the more frequent you see hurricanes. And so we have red areas right around Miami. So about every 6 years in Miami, you are going to experience a hurricane on average. Our smallest number is the Outer Banks of North Carolina. So we see, like in this graphic, that these storms tend to curve and go back out into the Atlantic, but a lot of times they'll just kind of clip North Carolina there. And so that's our smallest return period. If you live in New York, you'd see a hurricane about every 20 years on average, and then you're every 50 years on average up in New England. And New Orleans is another area that's frequently hit. So it's just some more kind of statistics to orient yourself about how often these things occur. This actually has the typhoon label over here. So these are where they're called typhoons. These are where they're called cyclones, and then this is where they're called hurricanes. And tropical cyclone just encompasses everything. So globally, on average, we see 86 tropical storms, which just means it's one of these rotating, tropical cyclone systems that has wind speeds of at least 39 miles per hour. And then once you're above 73 miles per hour, then it's officially a hurricane or a typhoon or a severe tropical cyclone. All means the same thing. And so we see on average per year 47 of those globally. And we see the most of those in the Northwest Pacific. So that's this basin here. And then it looks like Northeast Pacific. So this area, these hurricanes don't tend to get a lot of attention because they don't hit anything unless they end up hitting Hawaii, but they just kind of go off and don't do much in terms of damage, but there's plenty there. And then in the Atlantic basin, the ones that we hear the most about, we on average get 6.4 hurricanes per year here. So we categorize hurricanes by their intensity in terms of this Saffir-Simpson scale. So that's a scale from 1 to 5, and it is mostly based on wind speed. So this is in miles per hour. So category 1 is the 74 miles per hour to 95 miles per hour. That's the wind speed within the storm. So not like how fast it's moving or anything like that. It's the wind speed within the storm. And then up to 110 miles per hour is category 2, 129 miles per hour is category 3, 156 miles per hour is category 4, and above 156 miles per hour is category 5. And so here's a graphic of the damage associated with those. And so it kind of accelerates quickly, where the difference between, so 1 is not all that bad, and the difference between 1 and 2 is not all that great. But then once you get up here in 3, 4, 5, then you're talking really, devastating damage. And we consider anything that's above 2, so 3, 4, and 5 are considered major hurricanes. And you'll see that distinction quite a bit when we talk about how climate change is affecting these systems. So kind of going up into category 1, that looks like you're just kind of blowing leaves off. Category 2, getting the shingles off there. Category 3 is when you're actually blowing down trees, and you can completely wipe buildings off foundations when you're in category 4 and category 5. So here's some pictures of that wind type damage. On the left is it's kind of a famous hurricane from early, so 1900, Galveston, Texas. Just total devastation from that 1900 Galveston hurricane. And then on the right is from Hurricane Ike, which is in the same location in 2008, so on a Gulf Coast. So wind is a big factor in terms of the damage that we see. And this is just showing where various hurricanes have hit historically on the East Coast and their categories. So categories at the time of landfall. So category 5 at the time of landfall is extremely rare. So one instance of that was Hurricane Andrew in 1992, very famous because it hit Miami as a category 5. Hurricane Katrina was a category 5 right before landfall, but ended up being a category 3 right at landfall. And Hurricane Katrina actually first hit Florida over here as a category 2, and then went out into the Gulf of Mexico and kind of regained strength over a bunch of very warm sea surface temperatures, and then hit New Orleans. Sandy, category 1 at the time of landfall. So that was a combination of hitting a location where there wasn't a lot of preparation for hurricane conditions, and very, very densely populated, and it was high tide, and so there was a bunch of other factors that caused that to be so devastating. Yeah, and then we can see this kind of protection from North Carolina for Delaware and Maryland and New Jersey there. So a big part of the damage from hurricanes is from this wind speed, and we see this reflected in the fact that hurricanes are like the most damaging weather or climate extreme of all those things that I've talked about in that diagram. Hurricanes tend to cause the most damage in terms of monetary losses, and so this is the NOAA, National Oceanic and Atmospheric Administration, keeps track of billion-dollar disasters, any weather climate event that causes $1 billion or more in damage. This is from 1980 to 2021, and this is ranked in terms of the most damage. So total CPI adjusted, consumer price index adjusted. So that means it's adjusted for inflation. And looking at all of the worst events, it's like 1, 2, 3, 4, 5, 6, 7. So the top 7 are all tropical cyclones. So it goes Katrina, Harvey, Maria. So that was Puerto Rico is where the damage is coming from, because this is all U.S. Damage. Then Sandy, Ida, Irma, Andrew. And then we have our first non-tropical cyclone, Midwest flooding of 1993. So that was river flooding in the Midwest due to a ton of snow and the snow melting all at once. But then we're back into tropical cyclones. So then these are all tropical cyclones. And then we have our 2018 Western wildfire. So that's mostly the destruction of paradise from the Camp Fire there. And we're getting into some other things, so then wildfires come in. But you can just see that it's dominated by tropical cyclones as being the most damaging type of weather or climate extreme that we see. And so in addition to the wind, it's the flooding that comes about from these things. And you can kind of see that here with just how extreme the amount of flooding can be. And a big part of that is the storm surge, that when you have really fast winds, it piles up the water ahead of the storm, and then just pushes all that water inland when it hits the coast. And it's just a huge amount. Like, so this is just showing that category 5 tropical cyclones can be like 20 feet of water inundation. So flooding is a big part of these. And we've seen that we talked about Hurricane Harvey, most of this is rainfall. So there's the rain aspect, and then there's the storm surge, the ocean coming in. This is LaGuardia Airport in New York after Hurricane Sandy, and then here's downtown New Orleans. So the wind plus the flooding is what makes these so damaging. So that's our tropical cyclones just in the current climate. And so let's talk about how increasing greenhouse gas concentrations might affect these things. It's not so obvious what to look at, like what's our measure, what's our metric to look at, because with global temperature, it's just global temperature, you just average global temperature together, and that increases when you increase greenhouse gas concentrations. But what could be some things that change in a warmed climate for tropical cyclones? So I wrote down several things. It's not exhaustive, but these are characteristics that I've seen studies look into. So there's the existence. So this would be like that return period. So frequency of tropical cyclones. You just count them. How many are there in a given basin or globally each year? Is that changing? Would that change with changes in climate? You can think about the size, like the average size of each tropical cyclone. Could that be getting bigger or smaller as the climate is changing? The duration, so how long each tropical cyclone lasts. You could have a situation where tropical cyclones have shorter lifetimes or longer lifetimes as the climate changes. There's the wind speed. So we typically just think of the strength of the storm, usually characterized by wind speed. And that's why we have these categories like set up with differences in wind speed. Then there's the rain rate, how much rain is coming out of the storm. Storm surge, how much water is being pushed in by the storm. So ocean water being pushed in by the winds of the storm. And the location, so where they occur. So that might be that the average track location of the storms changes as the climate changes. And another thing that I've seen is rates of intensification. So that's just how fast a storm can go from nothing to category 4 or 5. And another one is forward motion, or the speed of the storm. How fast is it going? So that could be, if the average speed increased, that could be bad in terms of it could affect more things inland, because it can kind of get further inland before it weakens, because all storms kind of weaken as they hit land, because you're cutting off that warm sea surface temperature fuel for the storm. Or it could be worse if they slowed down, because then it can just kind of sit there. And that's what happened with Hurricane Harvey, is it just sat there and dumps rain on one location for a very long time. So there's trade-offs with that. But so these are all things that I've seen studies on. So we're not going to go into each one of these things, but it's just like kind of the point I'm making is that it's more complicated and nuanced when you're talking about phenomena like this, because some things can be going in one direction and some things could be going in another direction, and some things can be controversial, but then other things are less controversial. And so we'll see which things we have the most confidence in that are actually changing. So first, just kind of some basic theory about what we would expect from changes in tropical cyclones. So there's kind of like 3 main things that tropical cyclones like. So the one thing that we've already been seeing is that they really like warm sea surface temperatures. So we can see that both geographically where they take place. So they occur where there's the warmest sea surface temperatures. And there's actually like a threshold around 27 degrees Celsius. And we only really see tropical cyclones or major tropical cyclones when sea surface temperatures are above that value. And so we can see that geographically, but then we can also see that in the seasonal cycle. So this is a graph of the average number of storms per 100 years that just exist, hurricanes and tropical cyclones and hurricanes. This is in the Atlantic basin. And we see that we have this very sharp peak around September 10th. And that coincides very much with the warmest sea surface temperatures in the Atlantic. So that's delayed from the summer solstice for the same reason that we talked about with why the afternoon temperature is delayed a few hours after solar noon, because we still have more energy coming in than out up until around September 10th, and then it flips signs. But anyway, the point is that the warmest sea surface temperatures occur in that region in the fall, in the late summer, early fall, and that's when we have the most hurricanes. And so that, of course, is increasing as the globe gets warmer. So everywhere sea surface temperatures are increasing. This is showing the trend in global temperature, which over the ocean is essentially the same thing as sea surface temperatures. And so everywhere we see an increase in sea surface temperatures. So that should definitely cause there to be, by itself, that should cause there to be more and stronger tropical cyclones. But there are a couple of things changing in the atmosphere that might be countervailing factors or mitigating factors that would cancel out some of the changes from warmer sea surface temperatures. So I won't go into the details of these, but one of them is, so these are also both things that tropical cyclones like. One of them is a tranquil atmosphere. And another way of saying that in meteorology, we say low wind shear. And so wind shear is when you have some wind at one level in the atmosphere, and you have a lot more wind and like a higher level of the atmosphere. And so you kind of imagine that that type of environment is not great for a tropical cyclone to form into, because those prevailing winds will kind of turn the whole system over and make it so that it can't form with a lot of strength. So we actually think that, or modeling shows that wind shear, at least in the Atlantic, should increase under climate change, under global warming. And so that would be something that might make it so that you have a less conducive environment for tropical cyclones. Another thing is the lapse rates of the atmosphere, which is just how fast temperatures decrease with height. Tropical cyclones like temperatures to decrease with height very quickly, because that causes there to be a lot of potential energy for them to tap into. And as it gets warmer, that decrease in temperature with height is not as extreme. That by itself would cause tropical cyclones to be less severe. So we have a situation where not everything is going in the same direction. And so it's not obvious just kind of from first principles what would happen to tropical cyclones. You kind of have to use modeling and a bunch of other clues to see what's winning in terms of changing the characteristics of tropical cyclones. So let's first look at observations and see what the trends look like for a couple of these characteristics. So I'm going to show some graphs, some observed changes in tropical cyclone frequency and this index of tropical cyclone strength from the Bulletin of American Meteorological Society's State of the Climate report, which comes out every year and kind of documents every single phenomena globally and how it's changing. So this is what it looks like in terms of global annual count of named tropical cyclones. So that's in this this lightest color. And then cyclones would be anything that's like a hurricane strength or more. And then major cyclones would be anything that's category 3, 4, or 5 or more. And this goes back to 1990. There's other records that go back further, but this goes back to 1990 because that's the time period when they can calculate this other metric called ACE, which I just kind of screen captured the Wikipedia entry over here. ACE is accumulated cyclone energy. And it's basically taking all of the cyclones, all the tropical cyclones, looking at their wind speed over their entire lifetime. And you square all the wind speeds, and then you add up all of those numbers. And the idea is that that's kind of taking into account a bunch of things simultaneously. Like it's taking into account how long the tropical cyclone lasts, because the longer it is, the more values that you would add up. And then they square the wind speed, taking it and raising it to the power 2, because kinetic energy is proportional to wind speed squared. So when you double wind speed, you get 4 times more kinetic energy in that wind. And so it kind of is like you have 4 times more damage potential when you double wind speed. And actually we can see that. I'm going to go back to one of these graphics here. When I was showing all of the damage from these historical tropical storms, over here this shows mean damage in millions of dollars for these different categories. And you can see that there's a very nonlinear relationship. It kind of falls apart at category 5 because there's only three values in this data set, and if a category 5 hits an area with nothing to damage, then that would totally skew it. But if you have enough in here, you can see that the damage goes from, on average, so 2,000 million, so 2 billion, 4 billion, 12 billion, 43 billion when you go from category 1, 2, 3, 4. So it's not like it's a linear relationship where it goes 2, 4, 6, 8. It's very exponential. And so that's related to this idea of squaring the wind speeds to get an idea of how much energy, how much damage potential is in tropical cyclones. But when you look globally, it's basically flat. So we see maybe an increase since 2010 of total named storms, maybe a little increase in major cyclones globally. Not much change, if anything. in terms of accumulated cyclone energy. So in terms of these metrics, which are mostly based on wind speed, observations do not really show a change in those things over the past 30 years. It does matter a little bit basin by basin. So if we look at our North Atlantic basin, this is a similar thing. So we're showing named storms, hurricanes, major hurricanes. Then there is kind of we have a longer record here going back to 1950. Then over the past 30 years, there is what looks to be an increase in total named storms, and then maybe an increase in major hurricanes. 2020 was this record year in all of these metrics. 2021 had 21 here, had 21 total storms, so it would be like back down here. And how many hurricanes? I think it was 7. So this would be like back down here. And then major, I think, was 4. So like that. So potentially some observed increase in the frequency of total storms in this basin. And then here's our ACE metric again, which kind of shows this decrease and then this increase again. And so in this basin, the kind of controversy in the scientific literature has been whether or not this increase was due to increasing greenhouse gas concentrations or changes in a local ocean circulation called the Atlantic multidecadal oscillation. And so that's just an ocean circulation that causes sea surface temperatures to rise and fall over multi-decadal periods. And so there's a lot of kind of back and forth in the scientific literature on whether or not this can be attributed to that ocean circulation or increased greenhouse gas concentrations. And I think the jury is still out on that. But if it's flat globally and there's an increase in this basin, then some of the other basins must either be decreasing or kind of everything else has to be pretty much flat. And so that's what we see when we look at these other basins is, this is the one with the most activity. And we see our annual counts basically flat with some variability. And here's our ACE index again, how much total energy we see in these tropical cyclones, basically flat. Looking at these other basins, here's the North Indian Ocean. Maybe increase in ACE recently, but could just be kind of a coincidence in 2019 being high. Looking at the South Indian Ocean, again, basically flat. And then the Southwest Pacific, if anything, looks like a decrease in these metrics. So these are metrics that are mostly based on wind speed. And so if we go back to our characteristics here, the strength, wind speed, at least in terms of observations, historically, there's not a lot of evidence that that's changing much. And I want to point out that you will often see, if you pay attention to these things in the news, you'll see a lot of citations of the economic damage caused by hurricanes and how that's increasing by a lot. And so this is, again, from that NOAA billion-dollar disaster type analysis. This is looking at tropical cyclones through time from 1980 to 2021. And this is the number of billion-dollar disasters, so how many occur each year. And we do see, if we look at early in the record, there's just 1, 2, 3, 4, 5, 6, 7 billion-dollar disasters here in the first 10 years. And then recently, you're getting 7 in 1 year. So that's like this huge increase recently. And this is another analysis. This is total damage, so not the number of billion-dollar disasters, but the total economic damage. And going back all the way back to 1900, we see this huge increase recently, especially post 2000. And you might think oh, maybe that's because it's not inflation adjusted or something like that. But no, both of these are inflation adjusted. This is CPI adjusted, consumer price index adjusted. And then this says in US 2019 dollars. So it doesn't have to do with inflation. But it's kind of interesting, why would this be increasing so dramatically if we don't really see an increase in these wind metrics? So it's inflation adjustment is one thing, but that's not accounting for just there being more value at risk, that being more things to damage, more value to damage. So you can kind of see that in like, GDP metrics, for example, that the economy since the 1960s in the United States has, gotten way, way, way bigger. Like this is showing like 20 times bigger. And that's, this is current US dollars. It's not an inflation thing. It's saying that there's just that much more trade of value going on. And that would be related to how much capital there is, how much physical infrastructure there is to damage. And so that gets called in the papers that look at this, the expanding bullseye effect. And this is kind of just an illustration of that. So imagining so we have a river in blue here, and we have a floodplain hatched, and imagining a city changing over time, where here we have basically looking at the same flood affecting the city at different times, but the city is getting bigger and bigger and bigger over time. So kind of the bullseye that the flood can hit is expanding. So you have just like the increase in population, and then you have the increase in value that can be damaged. And this shows that this is particularly true with tropical cyclones, with hurricanes, that the population in the United States since 1900 has increased by 4.4 times, but the population on the Florida coast has increased 68 times over since 1900. So it's not even just the population itself is increasing, it's the population that's exposed to tropical cyclones is increasing dramatically. And we can see that like in a picture like this. This is Miami Beach in 1925 and 2017. And so of course you get way more damage when the same system hits the same location later in time. And so this is a paper that looks at that and basically takes this raw damage from tropical cyclones and then tries to correct using various statistical methods for the increase in how much value is at risk. And so this is what that would look like according to their estimate in terms of how much damage you get every year back to 1900. So then instead of looking like this huge increase trend, it looks like kind of flat. We had this minimum in the 1980s and then back up later. And then if you look at then the hurricanes, this again, it's imagining that like we have current infrastructure, and then the same hurricanes were hitting the same current infrastructure over this whole period from back to like 1900. And then this is then ranking those in terms of how much damage they would have caused basically if they hit today. And so now, instead of all of those most recent hurricanes that we looked at before, like Maria and Sandy and Katrina being at the very top, then we have some of these other ones like this 1900 Galveston hurricane and this 1926 Greater Miami hurricane, and then there's Katrina again, but then we have a 1915 Galveston, the 1992 Andrew, there's Sandy. So that's just something to keep in mind when we're looking at these damage estimates and how those can show this very dramatic spike when we don't necessarily see a change in at least the wind speed metric for these tropical cyclones. But when we do modeling of these systems, there are some other things that we think are changing, and we're more sure of climate change's impact on those things. And so one of them is this characteristic that I talked about with Hurricane Harvey, and this is this kind of same idea applied to Hurricane Katrina, and that's just that the rainfall rate should increase in a warmer climate when there is a tropical cyclone. And this is completely tied to this idea that the atmosphere can hold more water vapor. I said 6% per degree Celsius increase. You'll sometimes see 7%. And that means that there is just going to, the warmer it is, if there is a tropical cyclone, there is more water there to rain out. And usually tropical cyclones then essentially rain out all the water that's available. And so there's very good, solid theoretical and modeling evidence that rain rates should increase as it gets warmer. So rain rates and tropical cyclones. And this is kind of summarizing that along with that other metric of wind speed. So category 4 and 5 tropical cyclones. So we'll just kind of go through this. So here, first let's look at global. So this is looking at modeling evidence of 4 different tropical cyclone metrics. So we have 1, 2, 3, 4, and how we think they should change. This is at the end of the century relative to today under a high emission scenario. So are they going to change in the positive direction or the negative direction? Is it more or less? And so 1, 2, 3, 4 are, 1 is frequency, how many you see. 2 is the strongest storm frequency. So now we have 4 and 5, category 4 and 5 tropical cyclone frequency. 3 is maximum lifetime intensity. so how fast the winds are at the fastest point. And then 4 is precipitation rate. So globally, the best estimate is that all tropical cyclone frequency occurrence should actually decrease. That's what the models suggest anyway. So about a 20% decrease in total tropical cyclones, but an increase in the most intense tropical cyclones. So the category 4 and 5 looks like increase of, I don't know, 15% or something like that. And then if you kind of average these together, that's what this lifetime maximum intensity thing would be. So a smaller increase in that. But then precipitation rate is an increase, again, of 15, 20%. So if we look at like basin by basin, we see that there's a lot of uncertainty in, for example, this number 1 and number 2. So especially number 1, we have these large error bars where the North Indian Ocean, it's saying like it could be an increase in total frequency of 50% down to like negative 40%. We have these error bars that cross 0 or touch 0 in most of these basins, basically saying that we don't know how the frequency of tropical cyclones will change. But if you look at precipitation rate in every single basin, the error bar does not touch 0. So that means that we think everywhere precipitation rate should increase when there is a tropical cyclone. And again, that just comes from the fact that there's more water available to rain out in a warmer atmosphere. So that's one of the more robust findings that we're kind of the most sure of with tropical cyclones. And so that could also be contributing to this increase in damage that we're seeing recently from tropical cyclones. And the other component of that, the flooding component, you get flooding from the rain, but I showed you get flooding from the storm surge as well. And we know that should be worse under climate change because sea level is rising. So this is from the most recent IPCC report, 1950 sea level rise up to 2100. This is meters globally. And so we have this kind of big range, but we know that humans are causing sea levels to rise because the ocean just expands as it gets warmer and because we're melting our ice sheets. So we're very sure about the human contribution to that. And as sea levels rise, then each inch of sea level rise creates much more potential for inland inundation, depending on the local geography of the coast and everything like that. But that means that flooding potential becomes much greater as it gets warmer, both because of increased rain rate and because of increased sea level. So this is a paragraph kind of summarizing our best knowledge of how tropical cyclones should change under climate change from one of the recent IPCC reports. And they say can be summarized as follows. There's basically 3 things. 1, 2, 3. So the first one, and they have these confidence levels. The first one is there's medium confidence that the proportion of tropical cyclones that reach category 4 and 5, so that reach the highest severity levels, will increase, and that the average intensity of tropical cyclones will increase by 1 to 10% under 2 degrees Celsius warming. And that average precipitation rates for a given storm will increase by at least 7% per degree Celsius warming. So that's the same. I was using 6%, but 7% is also one that's used. So that's that same idea that you get 7% increase in available moisture per degree Celsius warming. And then they use it, I kind of find this confusing a little bit. They use this proportion of tropical cyclones. There's medium confidence that the proportion of category 4 and 5 will increase. Communication-wise, that's not great because you can have an increase in proportion of 4 and 5 by just zeroing out your 1, 2, 3, right? Like, so if we just had no more category 1, 2, 3s, then now 100% of our storms are category 4 and 5, but you didn't actually increase, impacts from that. Or you could keep your category 1, 2, 3s the same and, double your 4 and 5s, and then you'd have this increase of impact. That's a lot, but both of those are changes in proportion. And I think that they do that because they can get higher confidence in the change in proportion, but it's more meaningful to just count like what's the frequency of 4 and 5. But anyway, the most robust part of this is this increase in precipitation rates. And then there's low confidence in how global tropical cyclone frequency, just the counts, will change, but most modeling studies project some decrease in global tropical cyclone frequency. And most of that decrease is in the 1, 2, 3s, which is why this proportion thing comes in up here. But then in addition to the increased precipitation rates, we have this sea level rise will lead to higher storm surge levels for tropical cyclones that do occur, assuming all other factors are unchanged. So to summarize the summary, the safest statement that we can say about tropical cyclones and climate change is that increased greenhouse gas concentrations will lead to higher sea levels and higher rain rates, which will make flooding more severe when tropical cyclones do occur. So going back to our characteristics, it's basically these two things that we're most sure about increasing under climate change. And then frequency possibly going down. Size, there's not much evidence that size should change. There's not much evidence that duration should change. There's some evidence in location that this makes sense, right? That as it gets warmer, you have more area with warm enough sea surface temperatures to support tropical cyclones. And so there's some evidence that there's like a northward shift in the northern hemisphere of where tropical cyclones can occur. There's some evidence that the rate of intensification has increased, and there's some evidence that the forward motion speed has decreased. So that would exacerbate this rain rate problem like that we saw with Hurricane Harvey. But I just mentioned those because you'll see various articles on these other characteristics, but it's really these two things are the things that current climate science is most sure about.